So welcome everyone. Tonight's topic is human response to hurdles, Fermi, Drake, Kessler, and Zoo, and a couple of extras. So we'll get to that stuff in a while, but first we're going to do the news. So the James Webb Space Telescope is still aligning itself. They're still working on the spectroscopy aspects of it with the NIRCam and the NIRSpec instruments. Last I looked, they were adjusting things by tenths of a millimeter in the distance that the mirrors are traveling. They've got it all pointing in the same direction. They're now trying to get them all in the same phase. So the focal distance would be identical down to a very small fraction of a millimeter. And everything has to get its PR value in the news to show that it's still out there and doing its things. The NASA Space Launch System will be stacking up a Artemis lunar launch vehicle onto a crawler and driving it out to the launch tower to do some what they call wet rehearsal testing. This is where they'll fill it up with propellants and it won't go anywhere. They'll fill it up, make sure everything is pressure tight, and then drain it all back down and take it back into the building. But this is their way of saying, Congress, thank you for the NASA funding, and here's what we did with it. The wet test is for later in March, but the actual launch date is to be defined. And the initial launch will not be with people on board. It will be with a dummy capsule that just has weight in it to test out the launch vehicle. So yes, SLS is still a thing in the budget, and so is Artemis. And as if 3.14159 ... whatever, Pi Day is coming up, and NASA does an annual STEM event for Pi Day, a little math, exercise the youthful brains. So Pi Day. And as I was mentioning, everything's got to have its little PR value. And the Hubble Space Telescope is no different. This is a very lovely image that they have here from Hubble. It's not current. It's a lovely image, but the image dates back to, what was it, 2015. 2015 was when the image was taken. There's a class of objects called Herbig-Haro objects, HH objects. This is HH object number 34. And what that class refers to is these are fairly recent, as recent goes, stars that are doing things. They're moving, they're clearing out clouds, they're spewing plasma streams as they spin up very fast. So nice picture of a
normally those objects are large stars too.
And it hasn't launched yet. It's not launching for a little while. They're still assembling bits and pieces of it. But NASA's Psyche spacecraft, unmanned probe, got its wings, so to speak, its solar sails. The solar panels are actually in the form of a giant X. So what you're looking at here in the picture is just one of the two for one side, and they've got three others to mount that are about the same size. When you get that far out, in proximity to the asteroid belt, you tend to have a lot less sunlight, so you need a lot bigger solar panels. The last time they had solar panels this large on a deep spacecraft was Juno, which is in various orbits around Jupiter. And I guess given the announcement of budget approvals, NASA also has to say things like, hey, here we are taking the money you gave us, and we're starting to assemble the Europa Clipper spacecraft. This is going to be something that is sent to Jupiter's moon, Europa. Unfortunately, as I've often said, they don't send the right instruments to make a conclusive decision. The Europa Clipper will be no different. The instruments they're sending will be able to determine if the atmospheric environment is conducive towards life, but they're taking no sensors that could biologically confirm life, which if you're doing spectroscopy at that closer range, there's going to be gases coming off of Europa or salts in the surface of Europa that might be indicative of life. But NASA is stating right up front, well before they launched this spacecraft, we're not going there with this instrument to make any conclusions about whether or not there's life in association with Europa.
Anyway, this world is not ours.
Yes, the landlord owns this one. We're supposed to get all the others, though. And it's kind of a follow-up to our Earth timeline last week. I found this one interesting. They found a fossil of a very tiny, ancient octopus. It had 10 arms, not 8, but other than that, it was pretty much an octopus. It's kind of interesting that the fossil was dated before the central time period of the dinosaur age, which says that an octopus, which is classified as a fairly intelligent creature, actually existed before the main stream of dinosaurs. So that would say that intelligent life can form earlier. Now, maybe it's not sentient, maybe it's not technologically advanced, but complex life with brain power, so to speak.
But wasn't that one of the premises between on Alien Resident?
Resident Alien, yes.
Yeah, Resident Alien, yeah.
Yes, is that one of his ancestors was an octopus, and when a stupid human killed the octopus, he had a memorial service for him by eating him.
Yeah, I thought it was a dog that got the.
No, it's an octopus, and it was as if he was speaking to an earlier genetic example of his own species.
Yeah, I like Nathan Failure, and I was sorry to see him taken off the show so suddenly.
I'm sure he was under contract for a limited term because he's working other angles.
Yeah, he's working the rookie.
Yeah. And as I was mentioning Earth Timeline, I did edit the video and post it to our YouTube site. So you can, if you missed it or you want to go back and see pieces of it, you can go back and watch it.
5 views, very nice. One of those were mine.
Yeah, I saw your signaling to your mother. You're on TV. So heads up, daylight savings time kicks in tomorrow, 2 a.m.
Oh, not tonight?
Well, very late tonight after midnight, yes. But 2 a.m. tomorrow. Spring ahead. And I've seen, as usual, there was an annual push to let's get rid of daylight savings time, but not really get rid of it, just convert our normal time to be the time that daylight savings time is.
Yeah, Marco Rubio wants to set it like a half an hour earlier and keep it that way.
Yeah, well, ask people in the Phoenix, Arizona area how's that going out for them. But for the people that go, we want to take Eastern Standard Time, move it ahead an hour, which makes it Eastern Daylight Time, and then create a new time zone for that. Like, why don't you just call it Atlantic Time Zone? Because that's what it would be.
I always hated that because when they changed it to being darker earlier,
Yeah.
now I had to deal with going to school with kids running across the street in dark clothing.
Yep. Well,
They have more heart attacks, more deaths, all kinds of things.
yeah.
Uh,
I think that's due to the change itself. I don't think that's due to the fact that it's 1 hour earlier or later, because then you'd find things like people in the mountain time zone die more frequently than do people in the Eastern time zone because it's earlier. And that's not statistically accurate. So it's just the transition itself.
Yes, I would like it to stay the latter, you know, the daylight savings time. I don't like it changing.
Well, I've traveled enough internationally that I just think of it as an aspect of reality that time is not the same throughout the entire planet. However, here's a fun fact. Russia is a very east to west large nation, and they have one time zone throughout the year, which definitely means there are certain parts of the country that have a different daylight than others, even though they're in the same country and all in the same time zone.
Okay.
Yeah.
So, you can have your cake and then find out it's not too tasty to eat it too.
What time zone is the space station ISIS in?
I don't know what time zone the space station is on,
Zero.
but
It's UT.
Greenwich Mean Time. I would say that's also known as Universal Time or UT. I would say they're probably on UT because they go around the planet every 90 minutes. So what time zone do you want to align yourself with? Pick one. UTC just being easier.
They found an exoplanet that went around the sun in a day.
Oh yeah, those, when you get to smaller diameter stars, orange and red stars, in order for there to be planets that have the right temperature, they're very much closer to their star than our Earth is, and therefore their days are a lot shorter.
Do you think we'll be able to get the astronaut off of the space station?
Oh yeah,
Sure.
Okay.
Yeah.
SpaceX.
SpaceX is right. We'll fly up a broomstick and have them come back on a broomstick.
Well, I heard one person say we have the ability to change the orbit and all of that on the space station.
Well, it was simply a matter of a software update. SpaceX was never asked to be able to elevate the altitude of the space station. If you remember me discussing the docking ports on the space station and where the Russian docking ports are versus the US SpaceX docking ports, in order for you to take a spacecraft that docks at a US docking port and have it lift the space station, you have to adjust the propulsion trajectory for that spacecraft. And SpaceX was never tasked with that, so they didn't have the software to do it. So they've now been asked to update the software so that the next time a SpaceX Crew Dragon docks with the space station, it can be used to lift the space station. And so there's a little adjustment of fuel, there's a little adjustment of propulsion direction because they can steer the nozzle a little bit to loft the space station. So I don't see it as being a problem. And if Russia actually says they're going to abandon their use of the space station, we can always change the docking adapter on the Russian docking ports to be SpaceX compatible, and then the capsule can dock or move around to directly beneath the space station and more effectively lift it. And anyway, next Saturday, Helen and I will be down at Sea Grape Drive again for the final event of the winter 2022 schedule by the National Park Service at Big Cypress, March 19th. It starts at 8 p.m. Notice they say EDT because it's daylight saving time. Of course, there's another shorthand, which is you take out the S and the D and let people realize whether it is or isn't standard or daylight. So you just say ET for Eastern time zone. But no, we're going to have people put in the S's and the D's just to make things look different. Anyway, it'll start at 8 p.m. EDT or 8 p.m. ET. And I'm not going to play it, but this week there was the Lunar Planetary Science Committee's annual conference. And Helen, being a NASA Solar System ambassador and having street cred with Sophia, she was allowed to participate for free. Me as a normal street guy, if I wanted to come in, it would cost me over $300 if I was a student. And if I was not a student, it'd be over $400. So I said, I think they'll probably put it up on Zoom afterwards, so I won't be interacting live. So Helen, do you want to give us any insights from the LPSC?
No, the meeting wasn't, I didn't participate at the meeting. This was the people who just finished the meeting and they were giving the opinions, talking about the meeting. Those are for scientists, so that's not even for me. But then they have those meetings to explain, more like explain the money used on our institutions or what we are doing with the tax money. So that's how they explain what they're doing the science. It's basically like forget the young people to explain how they use the money, what kind of science. And you see like Caitlin and Paul, they were the elder one there for explaining what they do. One is British, the other one is American, and they are really good communicators. So the other two, Charissa is just brand new. She didn't even start her post-graduation. She's still undergraduate student. And Eva, she works for the rover Mars 2020. And she's kind of, she's good communicator, but she still, need to eat a little bit more beans and rice to get to the point of the other ones.
Yeah, the agenda and the abstracts of the papers were available online to the public. So I went out and perused some of those, and you could tell all the papers were oriented towards trendy science that says, I'm doing something, give me money to publish next year. So it was typical science confab. And also something Helen pointed out is NASA has got some instruments aboard the space station that allow them to do quantum entanglement scientific research. And they're trying to create a communications mechanism that will allow them to communicate via quantum entanglement from the Earth to the space station. And much like quantum computing, the entanglement data stream does not last all that long, well less than a minute. And they have a laser optical communications link on the space station that acts as the fallback and resynchronization. So that's what it's pointing out here is you've got a laser transmitter receiver and the quantum entanglement transducer, I guess it is, in the middle. But the Chinese space station has already done these sorts of experiments. Of course, they didn't report the results of them, but they were the first to claim that they had quantum entanglement communications between their space station and the Earth. Okay, any other news items that I might have missed?
I was listening to Space Nut. That's a podcast.
Yep.
So I don't know by the title, you don't know, but so they had a guest speaker on in February. So you may have already talked about it, but I didn't hear you say about it. But they said that there was a planet that they can't see, but they've been able to tell this information by the same things that we tell other things that we can't see by. That the planet has, that it's raining gems, that that their information is that there may be sapphires and gemstones being rained down in the atmosphere. And I thought that just sounded so beautiful. I don't think I want to be there while it was raining stones, but still, on the other hand,
they're microscopic in size. And by the way, they do that in our solar system, they believe, which is,
yes.
Is Uranus or Neptune. I think one of those two planets. Supposedly, when it rains, because of the temperature and pressure, it doesn't rain water, it rains microscopic diamonds.
Oh, diamonds. Now I hadn't heard them say anything about diamonds, so
yeah.
That was interesting. Though they did mention that it could be any kind of stones. They said other places had them. So you have heard of it. I don't know if you've talked about it.
I think a long time ago, Carl Sagan in Cosmos postulated that if the chemistry, the atmospheric pressure, and the temperature are just right, that if you have a carbon-rich atmosphere, that it will rain sapphires or diamonds as opposed to water. And
Yeah.
yeah, if everything is
But that is not,
just
not
right.
a good vacation spot, I promise you.
It's not.
Yeah, it's not a vacation spot. The second thing is,
No.
even if you were to go to Neptune, catch it when it's raining, and get yourself a giant scoop of diamonds, the amount of money it would cost you to get there, the time it would take you to get there, and the amount of money it would cost you to successfully get that scoop back to the Earth, you've already spent billions of dollars more than that scoop full of diamonds is going to bring you on the market.
And
Well,
you can
maybe. I
actually
mean, Russia
nowadays
right
make
now
that.
we're banned.
And
Right now
nowadays
we're
you
ban-
can actually make those scoops of diamonds in laboratories with the way much less expensive, like all the tools that use deposition diamonds.
Mhm.
It's like way much cheaper.
But aren't those cubics, or they're not
Tell
real
to buy.
diamonds?
No,
No,
no, no,
they're
they're
really
real
real.
diamonds. They are real diamonds. And in
Yeah.
fact, De Beers, who's, I guess you could say, the monopoly of the diamond market, De Beers,
Yep.
they actually went into an agreement with General Electric Corporation when GE started making man-made diamonds for microscopic wire gauges. In other words, if you take soft metals and you draw them through diamonds with a series of holes that get smaller and smaller, you can actually draw out very, very thin wire for use in things like,
Oh, cool.
solid state microscopic circuitry or quantum computers or such. And GE proclaimed that they can produce diamonds at the carat size level all day long, cheaply. And De Beers said, no, 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 not so fast.
And so it wasn't possible.
So they entered into an agreement where GE is okay producing the diamonds that they needed for drawing fine wire, so long as those diamonds were not allowed to get out into the jewelry market.
So there can be somebody else that'll come up and coming and.
Oh, it is.
Develop
It
it.
is. Anytime you have a technology that is fledgling that you think you can do something cheaply, if there's enough demand for it, somebody's going to create a newer, cheaper, faster technology that can do it at a much higher mass production level. And there are numerous companies out there now that they skip the whole making a diamond thing and then having to grind it down to something flat. They're now much the same way that they're making silicon wafers. They're now making diamond wafers. So and the diamond is not a gem. The diamond is a disc about 3 inches in diameter and very, very thin. And it's very high quality diamond. No surface defects, no chemical doping, just diamond. And that's going to be the next way to take circuits that are very hot and dissipate the heat, because diamond is very good at dissipating heat off of surfaces.
Will they still be girls' best friend?
I don't think so.
No, no.
Not these diamonds. No, these diamonds would be,
No,
3-inch
zircon.
diameter and very thin.
Zirconians are forever.
They can make all of the principal gemstones synthetically now, but the American, Gemological Society has found ways that they can always tell if they're natural or synthetic, and they do sell the synthetic openly, but they're worth much less money, like 1/8 or something like that. I saw an amazing video yesterday where people were buying rough diamonds from a diamond mine, emeralds. And what they had actually done is gone and bought synthetic emeralds and then got some of the base rock and chipped it away and glued it into the base
Oh my
rock,
gosh.
the synthetic one, with special glue, because they can even test the glue to see if it's glued in by using ultraviolet light and stuff. And so they try so hard. And they also, that you can also take amethyst and heat it up and turn it into citron. And they have all kinds of tricks for all of the gems now, but they can largely be discovered.
Well, I guess
Yeah.
it's the same people that buy NFTs with Bitcoins.
Yeah.
That's true.
The interesting part that I read a while back was that synthetic crystalline material, be it, gemstones or whatever. The synthetic ones in volume production are actually higher uniform quality than those occurring in nature
No
because
impurities.
no impurities, consistent temperature and pressure for long duration. There's no variations. So when they do X-ray crystallography and they look at the actual patterning of the bending of X-ray light within the crystals, they can actually see a more uniform pattern in the ones that are artificial but well made than the natural ones. So that's how you know, is that a natural diamond? Yes, it has defects. No, it has no defects. It's man-made.
And the other important thing is that is no slave labor, no pollution.
Yes, they're not blood diamonds.
no- Yeah.
Yes, they're not blood diamonds.
Now, the one thing I want to add about diamonds that I just heard, and I'm sure a lot of people have heard, and I don't know how many we were importing from Russia, but that was one of the things they just banned it from Russia was diamonds. I don't know if that's going to be a big thing to us in the United States or not.
That was in the news, yeah.
What? I didn't hear the answer to that.
I'm ruined. I can't trade in Russian diamonds.
Yeah. Think of it this way. Russia is a complex set of geographic regions because it's so wide east to west and so high north to south. And it has mountainous areas, valleys, all sorts of terrain. So if you're looking for any sorts of crystalline substances, minerals, you're probably going to find some of them in Russia in high quantity. Russia has oil, Russia has gold, Russia has platinum, Russia has diamonds, a bit of lithium, not as much as you'd think, but a bit of lithium as well. So it's always going to be a natural resource plentiful area, but that doesn't mean the rest of the planet is without them. Now, if you say, let's remove Russia and China, you've taken out a good portion of all of those materials. And then if you say, well, let's take out Africa and South America, that's really a lot of it. But that doesn't mean that the US doesn't have any. It just means that the supply in the US is much less. For example, in Arizona, north of the battery assembly plant for Tesla, Nevada, north of the battery assembly plant for Tesla is actually a rather considerable lithium mine. And so Tesla bought into that mine such that they can control being the only customer for that mine for a number of years. So even if Russia cuts off the lithium supply and China cuts off the lithium supply, then Tesla will likely still be able to make lithium iron phosphate batteries because iron is plentiful, phosphates are plentiful, and they have access to lithium, and they don't need as much nickel and cobalt. So where you get your stuff can define how much of an end product you can create. So welcome. Tonight's presentation is going to be Human Response to Hurdles, Fermi, Drake, Kessler, and Zoo. We've had conversations over the last few months involving certain topics like the Fermi Paradox, the Drake equation, the Kessler Syndrome, the Zoo hypothesis, and a couple of others, Dyson spheres and things like that. Well, not everyone is familiar with these terms, these concepts. So tonight I thought we'd just have a little vocabulary leveling session, and I would explain these things and why they exist and what they're based in, and the fact that maybe they're there for a reason, and the reason can go either direction as long as the mechanism is still obeyed. But we can create new ones in the future. But this is how the human thought process generally responds to such things. So we'll get into that. So it is normal for a human response to hurdles to either say, yep, we're going to get through this, no problem, and turn to and make it no longer a hurdle. Or it's hard stuff and it's going to cost money and it's going to take years and it's insurmountable. We'll never be able to conquer this. We'll never be able to get this done. It's just too big, too huge. So we'll, what we don't want to conquer, we'll identify as being incredulously insurmountable. And anybody that attempts it, it's okay for you to fail because we know you just can't do it. So science, engineering, and math will declare something insurmountable based upon what they currently know, and therefore it is forevermore insurmountable. But not really. If you give up progress and thinking about new and different things, and you don't go outside the box to think about stuff, then you're right. It probably is insurmountable forevermore. But anybody that attempts to conquer things that are declared insurmountable are presumably just wasting your time and money. You don't even need to think about that. Well, that's not the case. That's just how people feel about it currently. So anything that we've conquered in the past has been something where we turn to, we analyze it, maybe have to create some new science, new physics, new math. We analyze what it takes to do it, and we come up with a solution to the problem, and it's no longer insurmountable, and we go on with the next thing. Kind of like it was important to break the sound barrier to make military aircraft go faster and faster as a matter of national defense. So initially we thought it's going to be really hard, maybe impossible, for you to make an aircraft that can go faster than the speed of sound. But we really needed it, and it didn't matter how much money we're going to spend to conquer it. So we conquered it. So we broke the sound barrier. But now it's a matter of making the aircraft efficient enough and quiet enough. So NASA has a program for making commercial supersonic aircraft that are quieter and more efficient in their fuel consumption to be able to travel in excess of the speed of sound. So eventually it gets around to the commercial commodity, high volume, low price offering. And then what was once insurmountable forever becomes checkbox. Yep, we do that. So this is what we need to do. Another aspect in our lives that most people might not be familiar with is something called Moore's Law. It was a guy that founded Intel. His last name was Moore. Moore's Law came up as a result of, as we put more and more transistors on a single chip, a single integrated circuit die, we eventually ran out of space because the lines, the lithography, the drawing that we were making of the image of the chip, the lines were just too thick. So we had to get to thinner and thinner and thinner and thinner lines. How thin can you make them? Well, when you get to the point where an individual transistor is only 100 atoms, that's pretty small. How do you get it even smaller to make, instead of millions or hundreds of millions of transistors per die, and dies are now bigger and bigger. I think the 12 inches is probably the current one. How do you make even more transistors on that die? Well, you've got to change the color of light you're using to higher and higher energy, shorter wavelengths to make the lines thinner and thinner. But you run out of space again. Well, you start putting the transistors, if you can think of it as you cut a V as a cut into the material, and then instead of putting the transistors only on the top, you also put the transistors on the sidewalls. So it became 3D lithography. And now they've got it to the point where on the top, they've got a flat spot, and you put multiple layers of transistors at offsets. So they're now going with deep ultraviolet lithography and 3D vertical stacking of transistors. And now we're open-ended to the how many billions of transistors can we put on a single die. So computers get smaller and cheaper and faster and lower power consumption. So whenever something is insurmountable, you've got to ask, is it really, or is it just we need to spend some money and think up some new things. If it's, we can do this, if we just put our hearts and minds to it, then pretty much nothing's insurmountable forever. So that gets to the first one. And reading the history of this one, I found very interesting because I've had these sorts of conversations. So in a casual luncheon conversation in 1950 at Los Alamos National Labs by Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski, they were attending a conference and they got together and they were talking about some UFO report. And Edward Teller brings up this cartoon from the New Yorker magazine that was showing that little green men were responsible for disappearing trash cans in New York City. And they were jokingly saying, well, that's probably the little green men that were flying around in the UFO. So they were responsible for both of those things. And Enrico Fermi just blurts out, where are they? And since these guys knew Enrico and how his mind works, they said, oh, you're talking about the aliens. Where are they? Well, the presumption was if the universe is so vast and technologically advanced sentient life is so easy to arise, then where are they? Why aren't they calling us? Yeah, like we're important and they should be calling us. And why is there no evidence of their existence on Earth or elsewhere in our solar system? So they were creating the, if you really think life is easy to come by in the galaxy, they weren't even talking universe, they were just talking Milky Way galaxy. If life is so easy and sentient life is so easy, where are they? Well, they had to come up with a conclusion as to, well, if we can't see them, then they must not exist. So presumably, the Fermi Paradox provides a license to conclude that they must not exist, and therefore humans are the lone sentient species in the vastness of the universe. This is a giant ego stroke to the species that once thought it was the center of the universe and who has yet to conquer gravity or light speed. I always like the phrase, absence of evidence should not be presumed to imply evidence of absence. And the best example of that is the coelacanth. This was kind of like an ancient fish species, very large, that has gone extinct. And then they found a few of them off of Madagascar. And then they found out they're rather plentiful off of Madagascar. But that's the only place on planet Earth where we find them. So we had to keep looking before we found what doesn't exist. Now, the Fermi Paradox is based upon two presumptions. If either of these are incorrect, then the Fermi Paradox kind of falls apart. Number one is there are many intelligent species in the universe. Now, they said universe, but I know they were originally thinking the Milky Way galaxy. And if that's the case, why is there no evidence of them? Why aren't they phoning us? The second thing is that we are capable of detecting them if they're out there. It's kind of an arrogant presumption by a species that currently only communicates by modulating the electromagnetic spectrum, when we know now that there's a lot of gravity wave activity out there, kind of like a background gravity wave. If we can start picking up more of that and demodulating it, we might find that EM modulation is something that eventually you grow out of and you start using gravity wave modulation as your means of communication because it's far more reliable and easily penetrates across the universe. So for those people that think that I'm just, spouting hot air here, I actually have some evidence. Here's the cartoon from the New Yorker. It shows a flying saucer landing and returning the empty trash cans from the Department of Sanitation of the city of New York. And the cartoon was originally from 1950. And I have 3 of the badge photos from Los Alamos National Labs, and then one's just kind of a publicity photo. So in the upper left, you have Enrico. Bottom left, you have Ed Teller. In the upper right, you have Emil, and in the bottom right, you have Herb. Now, everybody knows that Enrico Fermi worked on the Manhattan Project for us to have Fat Man and Little Boy, the first atomic bombs that we, decided to drop on another country. But how many people know what Ed Teller is famous for? The hydrogen bomb.
The hydrogen bomb and stabbing Oppenheimer in the back and getting his security clearance removed.
Yes, and as a joke, what movie portrays Ed Teller? It was a Stanley Kubrick film. Let's just say the actor was Peter Sellers, and he was in a wheelchair, and he had a slight Nazi German leaning.
Yeah, that's Dr.
Love the
Strange.
war.
There you go. Dr. Strangelove,
Or how
I learned to love the bomb.
Edward Teller I don't remember Teller in it.
No, he was Peter Sellers in the wheelchair. He was the madman with the bomb.
with the crazy uncontrollable arm.
I thought
Yes.
that was Kissinger. That was Teller?
No. That movie came out way after Kissinger got involved in politics. That was Edward Teller.
Yeah.
Father of the hydrogen bomb.
So the only thing that you have to remember is Fermi Paradox. So it means that it's one thing or the other. So you have to choose, or we don't know how to detect them, or there are many species in the universe. So it's a paradox. One, you have to choose which one is the real one.
Well, actually, which one is the one that doesn't work, the one that's in error? So either, if there are many intelligent species in the universe, then we should be able to detect them. If we're unable to detect them, then it falls apart. If there aren't many intelligent species in the universe, it falls apart because we won't be able to detect them, even if we had the technology to do so. So that's why it's a paradox. So this is the barrier that says, this explains why we've not yet detected any advanced sentient life in our galaxy, let alone the universe. Is they don't exist, because otherwise we smart humans would be able to detect them. Really? And if they aren't using electromagnetic spectrum modulation, if they're using gravity wave modulation that we've just learned, there are all sorts of frequencies of gravity waves just out there in the universe. That's like saying, I'm a radio communicating species, and the other people around me on the planet are all using smoke signals, and they're more than 25 miles away. Therefore, because I can't pick up any of them on radio, they must not exist. Yeah. Okay, that's the first one. The next one was the Fermi Paradox started to lose some of its luster because, well, we started to find out how many stars there were just in our galaxy, and how many galaxies there were in the universe, and the quantity of stars, even if it's a low percentage, that have life on them. We're now talking about life being possible throughout the universe. So why can't we find them? Well, it's the great filter. They came up with this thing called the great filter. With this is kind of an add-on to the Fermi Paradox that says, well, if you think the Fermi Paradox is going to fall apart, here's why it doesn't. Well, you can't travel at near the speed of light, can't communicate it near the speed of light. Therefore, we're so far away from each other, we'll never be able to communicate, and that's why we can't detect them. So the beauty of the great filter is that as soon as you conquer one of these, you can add a new filter and still be on the lean side of, being able to talk to anyone. But as humans, we've already conquered many filters. And I list them here: spoken language, developing fire, compartmentalizing labor. I'll be the hunter, you be the gatherer of crops, and you be the person that runs the city government. And now we can have bigger cities. building cities, mass providing of agriculture, big farms for lots of people, printing so we don't forget anything, advanced mathematics so we can calculate things, so we can build things in quantity, scientific methods so we can progress under a prescribed plan, electronics, not necessarily solid state or computer electronics, but just basic stuff like AC power, motors, generators, those kinds of things. And then we get into the atomic and subatomic physics. So we can do things like fission for power, not for bombs, breaking the sound barrier so we can get to places faster, computers of ever increasing capacity, smaller size and lower cost, wireless mobile communication, and then expanding that out as a mesh of worldwide communications networks. We went from 2G to 3G to 4G to 5G. We're now talking about 6 and 7G, and the internet. Quantum scale materials that exhibit properties that we cannot see at a larger scale. Solar power, ion propulsion, and detection of gravity waves. And now we're in the second generation of gravity wave detection, where we're detecting them at a variety of frequencies. But there are things we have yet to conquer. Some of the newer stuff that we're thinking about are quantum computers, getting the qubits to last a long time and be reliable, fusion for electrical power generation to make it cheaper, more abundant, and safer in case somebody wants to come by and drop something on it. Maybe antimatter reactors. We might find that fusion only lasts for a while, and then we realize that if we can create antimatter, that an antimatter reactor might actually produce far more energy, cleaner and safer than fusion, because fusion, as we know, produces neutrons that destroy the containment vessel, unless, of course, you have the helium-3 from the moon. We might need a better understanding of the source of gravity, using gravity control to avoid aerodynamics. Things that fly in the air and don't have wings, jets, rudders, ailerons, all that stuff. I think we might have seen some of that. Modulation of gravity waves for communication over very long distances. And moving away from chemical to far longer lived forms of propulsion beyond ion, because ion is still a Newton's third law form of propulsion. And eventually, as I've stated in the past, interdimensional transportation. Once we get that, it's kind of like the panacea. So there are many great filters out there, and some of them we won't actually know exist as a filter until we approach them and realize, oh, we can't do this because we don't know it yet, we don't understand it yet, we don't have the physics for it, we don't have the math for it, we don't have the technology, we don't have the mass production, but those things are conquerable if we turn to.
Moreau, as I understood, the great filter is that whenever a civilization is like technological enough, that is the big risk of that civilization to self-destruct, and that would be the great filter.
No,
That's
no,
what I understood as the great filter.
No, the great filter is a generalized concept that says there are things that you will need to conquer to exist for a longer period of time and to progress further. The fact that you might blow yourself up when you discover nuclear weapons, or the fact that you might destroy your planet through bad management practices, are just additional filters. The fact that the great filter is there really as an add-on to the Fermi Paradox to say, yet another reason why we haven't detected anything. So all of these are part of, that's why they call it the great filter. And if they wanted to say self-destructive behavior, be it weaponry or ecological, they would just call it self-destructive behavior. But they called it the great filter because anytime you conquer one, we'll throw in another one. That's why it's the great filter. Okay, next up is Frank Drake's formula, the Drake equation. So if you think of the Fermi Paradox as not specific enough, and you want to come up with a number, a calculation, because the Fermi Paradox doesn't say, and tell me what the potential quantity of, advanced sentient species there are in the galaxy, you need a formula. So if you come up with a formula and you throw some factors in there and you make them multiplicative, so you don't have to deal with the floating, the fractional errors of divides, you can come up with a number. And if you want the number to be large, you can be liberal with the factors. If you want the number to be singular, as in humans are all there is, you can be deeply conservative on the values of the factors. But as we start to learn more and more about the galaxy and the universe around us, the factors start to go from postulated to more accurate. And as they do, the factors start to make the resultant number very large, as opposed to what some people want it to be is 1 and never more than 1. So as long as there are unknown values, we can easily diminish the result to singular, meaning just us, by being conservative in some of the parameters. And as soon as we find enough of the parameters where the number is going to be far greater than 1, we can throw in some new factors in the Drake equation to get back to a low number or 1. So here's Drake's equation. And Drake's a popular guy in radio astronomy. And in fact, monthly, the Society of Amateur Radio Astronomers has a casual conversation session. What's up in the news? What's up with you? What are you researching? What are you working on? What kind of equipment are you playing with? And this session is called Drake's Lounge, because Drake created this back when they used to meet face to face at the radio telescope, the radio astronomy auditoriums. So the parameter that you're looking for is N. N is the number of civilizations in our galaxy, not in the universe, with which communication might be possible. That's not, that we're talking, that's that we've detected them or they've detected us, or we are talking. But that's the idea, is the number of communication aware or intercommunicating species in our galaxy. So the first thing you have to start with is, well, if you're going to have a species, they got to be on a planet. The planet's got to be orbiting a star. How many stars do you have in your galaxy? The average rate of star formation in our galaxy. Now that you've got a star, how many of those have planets? Now that you have planets, how many of those have the environment that could potentially support life? And then of those, how many of them can actually develop life at all? And then of those, how many of those can actually develop intelligent life? In other words, civilizations, civilized life. And then once you have that, how many of those develop communication technology, and how long does it last? What is their window? And that's where I think Helen was referring to the great filter as, if you say everybody develops communication technology using the electromagnetic spectrum, it's so drop dead easy. But then they get into other things like war or bad taking care of their own planet, and they disappear. So the amount of time that they are able to communicate or produce radio signals or lasers that we can detect is small. Therefore, they were gone before we came along, or they existed for such a short period of time at the speed of light travel. By the time their signal actually reaches us, they're gone. So it presumes electromagnetic communication, and it presumes it's only our galaxy. And what constitutes intelligent life? Well, they have to be able to eventually develop technology that can communicate using the electromagnetic spectrum. So now that we have
the lowest calculation that I've seen is about 100 civilizations. So one of the conservatives that you can get to 100. Oh, you did it. Okay.
Oh, I did better than that. This is a static table. I took the original numbers that Drake and his folks came up with. The column that says original, that's the actual numbers. they thought that only a tenth of a year of stars was the number of stars that form per year. You know, every year of existence of the Milky Way, you only get 1/10 of a star. And now they found out, well, instead of a fraction of one, it's really more like 2 1/4. So you go from 0.1 to 2.25. And I'm looking at it as we just discovered that black holes can create stars with their shock waves and their jets. So I think that 2.25 needs to be more like a 3. But if you keep it as a 2.25, let's go down to the next one. How many of those stars have planets? Originally, they thought, well, maybe a third of the stars that we discover will have planets. And what they found out from the Kepler space probe is pretty much every star that we looked at had at least one planet. So it went from 0.35 to 1.0. So I'll keep it at 1.0. If there's a star, there's at least one planet. Now, of those planets, how many of them are good enough to, have life sustained on it? They originally thought every third planet, 3 planets, you're going to have life coming into existence. And the current value is a little down from that. Now, the reason for that is we found that there are a lot more planets around stars than we originally thought. So if there's more planets, not all of them will have an environment suitable for life. So we dropped the number down. So let's leave that one over in the sort of conservative side as 0.4. But I think that as we look out to not just yellow stars, but orange stars, which are far more plentiful than yellow stars like our sun, you're going to find there's a lot more possibility. Then would life develop on those planets where the environment is suitable? And the original factor was, yeah, if the environment's suitable, you're going to have life of some kind. Well, let's keep with that 1.0. But you'll see in a moment, you need a 0.5 in that rightmost column, because otherwise that 2 becomes a very much larger number. You can see in the original that at 1.0, you start getting to 788. So there should be 788 possible communicating species in our galaxy alone. And if there's billions of galaxies, you now have 788 billion species with which you can communicate once you break that light barrier problem. The next thing is intelligent life. How many of them get to the point where they become intelligent and create technology? Not yet radio technology, but just technology in general. They have an intelligent species. And the original number was, yeah, if they can get as far as life, they can probably become intelligent. We'll keep with that. But again, over in the right column, in order to get it down to a small number, you got to drop that 1.0 down to a 10th. Then the next one is, and they can communicate using the electromagnetic spectrum, modulating radio or light to communicate. They originally thought, well, only 0.15 of those that are intelligent will actually go on to develop, modulation of the electromagnetic spectrum of some kind. And what we found out was radio is rather simple. So we'll give that a 1.0. So I'll keep it with a 1.0. However, to get it down to even 2, you had to drop that 1.0 down to a 1/10. But here's where it really gets interesting. They originally thought that if you can communicate via the electromagnetic spectrum, that something will come along and whack you. You'll either destroy yourself or, an X-ray pulsar will obliterate your atmosphere, or an asteroid or comet will hit you and you'll self-destruct. Yeah, don't look up. So they originally earmarked that at 50,000 years. So from the point of time at which you have electromagnetic spectrum modulation as your means of communication until you aren't doing it anymore is 50,000 years. I'll keep with that in my what if, 50,000 years. But in order to shrink that number down from 45,000 closer to just one, meaning just us, you got to make it 500. But what they didn't consider was other factors, like, well, maybe eventually we'll give up on electromagnetic modulation and use gravity wave modulation. So the 50,000 might become several 100,000 once we give up the old cart of EM spectrum and start using gravity waves. So the numbers can go up. So in order to get that number in the right column down to 1, we have to go the other direction and arbitrarily curtail the values, as opposed to my what if, where I'm arbitrarily expanding the values by a little bit. And as soon as you do that, you start to realize the number gets to be quite large very fast. But you want to do a what if? I have a link over here. Let's see if this works. And
It works.
voila. So I now have a live spreadsheet. And I found out in order to get the 1.0 to be exactly 1.0, I had to narrow it down. I had to add new factors like, okay, so they're intelligent life, and they've developed electromagnetic spectrum modulation. Oh, but now they've got to have bilateral symmetry. And over here, I've made all of these 1.0s as being more progressive. But over here in the conservative column, to get that down to 1.0, meaning just us, thank you, Fermi, I had to start really restricting it. So they've got to have bilateral symmetry, which means the left half looks like the right half, kind of like us. And then, oh, sorry, no forearms, no, four legs. You've got to be bipedal like us. So more like us, more like us. And then, oh, I don't care if you're orbiting an orange star, you've got to have color vision, which moves you more towards, the yellow stars. And I've got to put very much smaller than 1 fractions in there to get that final end to be down to 1. And it still couldn't get down to 1. So if I take this one and I take it out, watch this. If I just make that one 1.0, now I've got 3.7. Well, if you're looking for 1, that's too high a number. That's unacceptable. So I started putting in, well, what value does it have to be? And I use this very last one as the great filter arbiter of how do I really get it down to 1, even if I have to stretch? Well, of all the ones that can do all those other things, oh, we only want to communicate in the FM radio spectrum. So now we're down to a little more than a quarter. Well, if you have almost 4 and you take a quarter of it, you get down to 1, just us. But let's say we go over here to my what if column. We're all 1s here. Let's say that instead of 50,000 years, it's 10,000 years. Well, that brings you up to 90,000 in our galaxy alone. Well, let's say you move from electromagnetic spectrum modulation to, I don't know, gravity wave modulation. So instead of having 10,000 years of communications, you broaden that out and say, let's bump it up by a factor in 100,000 years. You now have 900,000 intelligent, communicating civilizations in our galaxy alone, and we cannot communicate with them, not because of the speed of light, but because our technology is not sufficiently advanced to know how to talk with them. We're the
But
guys
Monroe,
with the smoke signals.
gravitational waves move in the speed of light. I think the only solution is not modulation of gravitational fields would be quantum communication.
Okay, let's say we use quantum communication.
Ta-da.
I think there are those of us that still believe quantum entanglement still is limited by the speed of light, but we'll say that, let's say it's not. Let's say we find out faster than light communications, not involving the electromagnetic spectrum and maybe not even involving gravity waves. And all of a sudden, 100,000 years sounds reasonable. Now we're at 900,000 civilizations that we cannot currently communicate with that likely exist. So
So the first two numbers, the rate of star formation and
Yep.
the number of planets are known. So we know that, like the last 10 years, we actually know those numbers precisely.
yeah, well, originally they postulated it at 1/10 when they created the equation. But then as we currently understand it, it's at 2.25.
And we, because of Kepler, we know that in average, every star has at least one planet.
Yes, but Kepler's original mission only looked at yellow stars. And what they found
No,
out when
after later, yeah.
what they found out on the Kepler-2 mission, when they broadened it out to look at orange stars, is a lot more of the orange stars had more than one planet. So the 2.25 needed to be bumped up. I just arbitrarily chose 3.0. We may find that it's actually higher than 3.0, because remember, Kepler only looked at a small patch of sky.
So now we put it lower where life is possible, because looking at 4 terrestrial planets that we have only one that is that has life for what we know, and then so the guesstimations is 0.4. And then the actual life, when developed, that guesstimation came from Earth, because from my presentation from last week, we have some evidence that life arose as soon as the planet acquired water. So it was in the very beginning. So the idea is that life is easy to come about.
Right, which is why originally they were at 3.0, then they went down to 0.4, and given the fact that they can find life farther and farther back, and we can now, as of what we found an octopus fossil, we can find that creatures that have sophisticated brains existed far sooner than we thought, not by billions of years, but maybe by hundreds of thousands of years. So that 0.4 needs to come up. But let's say
No, this is life is possible now for each planet. This is more like a calculation that we do. So in the case of ours, now what can go like is intelligent life as number 7, but even though 1 is a very high number, because let's see, you have to see what is the probability. Think about it, like we have 8 planets. Only one intelligent. Let's say that we find life on Mars, and we find life on Earth, and we find life in Venus. Let's say that we find life in Venus. So intelligent life arose just in one planet, so would be 0.3 or 0.4. So that number 1 would be too high of a number for every planet there.
okay, so you want the number to become much lower. I can get that. So we'll put it 0.5.
No, not the
Okay.
actual life. Oh, yeah, the actual life. So it won't be 1.75. So we have 4 planets. Okay. So life arose just in one. So it will be you divide. It would be 25.25.
Lovely. Keep being conservative. You still have 56,000 of them.
Yeah, I see.
Yeah.
Now,
So-
let's say the just extrapolation, because we haven't found yet, but it doesn't mean that there is not enough, things alive in those planets, or even in the moons of the larger planets. So let's see, you put there, like for every planet that is alive, maybe 10% would be coming, intelligent life. So put 0.1.
Okay, you've still got over 5,000 of them in our galaxy alone.
So then for communication. So if arrives life, intelligent life, I would keep the number one, because it's if it's intelligent life, we end up developing something. Maybe if you compare the octopus, the cephalopods and dolphins, and the only species that developed communication was ours. So let's see, put it 50%, so 0.5 on intelligent life, be able to communicate.
Okay, now you're left with 2,800.
Okay.
Yeah, you're not
Let's
getting
see.
anywhere near one anytime soon with those kind of numbers. You're going to have to
Yes.
arbitrarily crush it.
Yeah, so I'm being conservative and very like my guesstimation is quite precise for what I know, and it's still like the lowest that I've seen it that has used this number. It doesn't even have the new factors, just the original
Right,
factors.
here's the current factors.
It's
The current,
100, at least in
the
this
current-
galaxy, at least 100 civilizations.
the current factors, and I got these off of the current information for the Drake equation, as 45,000. The original numbers brought it down to 788. Now, as you can tell, the numbers earlier on are more and more accurate as time goes on. The other numbers are just estimates. But as soon as you say things like, there's almost 3,000 civilizations just in our galaxy alone.
Put in my what if, 20,000 years. Because we have 10,000, we are about to kill ourselves, but I'm gonna be hopeful. Put it 20,000 years surviving.
There's 563.
Okay.
That's still way more than one.
Yeah.
Yeah. So you're gonna have to come up with some new factors, like they've got to be bilateral symmetry. They've got to be bipeds. They've got to have color vision.
I don't even go. I keep with the original calculation. So yeah,
That's fine.
I could not lower the number.
I know.
I could not
That's-
lower the number.
That's the point of it. Is originally it was designed to make a small number, and they thought 788 would be a number that the naysayers would be comfortable with. And as time has moved on, the numbers have
Like,
actually gone up considerably.
naysayers like me cannot lower the number.
Yeah. Every time we find out more information through factual observational confirmation, the number goes up
Yeah,
considerably.
okay. So because I haven't worked in any of those 10, 11, and 12 factors. So
Mhm.
put 50% chance for each one and see if I can lower the number.
Oh, you will. Because if you right away say, if they can talk to us with radio, oh, but they've got to have bilateral symmetry. So no weird animals. So we'll just go 0.5. So the 563.
Because let's say we are not inviting the Vorta there.
Yeah.
We don't have bilateral symmetry. Our internal organs aren't bilateral.
Yeah, but
anything
from
with
the
radio
outside we are.
has bilateral symmetry.
Yeah, but from the outside we are.
Mostly.
So there's squids and octopi. That's what our extraterrestrials are.
Yeah. Well, that's why you come back and you say, well, they've got to be bipeds. No more octopus for you. So we'll say, let's make that 0.5. See, now we're down to 141. That's still a lot.
Yeah.
And they've got to be able to see the same. They've got to be able to see the same way we do. Unlike a lot of other things that live on this planet that can see in infrared and ultraviolet, and not so much in visual, they've got to see like we can. So we're going to drop that 0.5. Okay, now we're down to only 70.
Monroe, are
Yeah.
there any theories on the distribution or location within a given galaxy of this intelligent life? Like, are they more likely to appear in the outer arms or toward the center of the galaxy, randomly distributed, clustered, closer?
They're
Well,
going to be less likely to appear towards the very core of the galaxy because of the massive amount of energy emissions going on there would likely sterilize planets that were too close to the core. So there's a higher probability of life existing for a long period of time in the outer arms. And
Yeah, but I think it would be something like in between the middle, or like not too far from the outer skirt, or like in the middle range, like we are, because the outskirts of galaxies tend to have less chemistry, and without chemistry, you cannot make planets.
but they have stars.
They do have stars, but those
and they have-
stars
and they
in the
have-
outskirts are very old stars.
And they're
There's
metal,
no new formation.
but they're metal-rich stars.
No, they're metal poor. The outskirts has less chemistry. The outskirts that has, like, the farther it is, that is less available new chemistry. And the stars that we can see in the outskirts, especially the clusters, they are very, very old, and only like stars there are first or second generation. That is not enough chemistry to make planets in those.
When you say chemistry, Helen, when you're saying chemistry, we know that because of we're able to measure
Spectroscopy.
chemistry.
Yes, yes.
Spectroscopy.
So as like Carl Sagan used to say, we are stellar dust, we are stellar stuff. Because if you don't have consequence, like the first generation stars made the first simple chemistry, and then as the second generation made a little bit more chemistry, and our star is probably third generation or fourth generation, most likely third generation. So the thing is that when you have stars that are in the outskirts of the galaxy, there was less star formation and explosion of supernovas that enrich the clouds that form those stars. So it's probably that area was just like maybe recycling from older galaxies that the Milky Way stole the gas, and those stars are in the outskirts of the galaxy. So the bulk of the chemistry that's happening in the galaxies is from the center to a little bit past to the middle of the galaxy. If the galaxy has arms, because those galaxies there have no features, the gas doesn't move too much. They have like a regular orbits. They don't agglomerate. So there is a point that the galaxy gets old and there is no new stellar formation. So those galaxies don't count in chance to make more chemistry. So galaxies that have features or have lots of dust in the clouds, those are the ones that makes stars with planets.
But if you have an orange star that does have a metal-rich composition, then it will likely have planets around it that will be
Yes.
around and have maybe been around for many millions to maybe a billion years longer than our planet.
Yeah, no, if the star is about a billion years older than ours, it would have enough chemistry to do. But when you go like 2 to 3 billions older than our own star, those stars tend to be a little bit poor in metals. So
Yeah,
they wouldn't
those
be
are
able
going,
to form
those are going to be red dwarfs or brown dwarfs, which
No, even
don't-
larger stars that about the same size as our own, that
okay.
had long last, if they form a few billion years before our own galaxy, because you have to agglomerate in galaxies enough chemistry to make planets. If you don't have enough silicate, if you don't have enough carbon, if you don't have enough whatever you're finding in any planet, you cannot form planets. That's not possible. So older stars that started to form like way before ours, depending on the time that is a cutting point of those long-lived stars, they will be very poor in metal. They are long-lived, but they won't have planets.
Okay, so what we need is a new Drake equation that takes into account the additional information that we've uncovered regarding the composition of stars, what
Yeah.
elements they might have.
No, that's that's covered in the rate of the star, because this is a rate that stellar formation, because when you get very young galaxies, they're forming a lot stars, but when you get like older galaxies, and then they are slow down in the formation, and then they get, you know, a little bit lower information.
Well,
So it's like,
the Drake equation is only applicable to the Milky Way galaxy.
yes,
So
yes,
F sub P, or planets existing around stars, they went from 0.3 to what they now believe is 1.0. So if you need a metal-rich star or a multiple generation star in order to form planets, they're now saying that of the 2.25 that they have for forming planets, for forming stars, then every one of those is probably going to form planets. So they're not saying that there are stars without planets. They're saying every star is going to have at least one planet.
yes. From what we know in the Milky Way for the recent results, but
Right.
what we know now,
Right.
you have to remember that the rate of formation of stars in the past in the Milky Way was, you know, larger, but then the number of planets in each galaxy will be lower. Instead to be at least one, will be, you know, like one in every 8 or something like that. It depends how.
The original value for the equation was 0.1 for star formation. It is now 2.25.
Yeah.
So they went from a very low number to a much higher number. So they
Yes,
think that
but
the stellar
thought that-
formation is actually much more than they originally thought it was.
We thought our galaxy was smaller, it had less stars, and we
Yep.
thought that our galaxy was like way too slowing down from what we compare. And now this rate will change when we become Milkdromeda.
Yep. But I'm not worried about that many billions of years from now. Okay, are we done playing with this equation?
Yes.
Okay. I liked it. I'm going to save it. Now we can get back to the presentation. As if by magic. So here's one you might have heard of, the Kardashev scale. This one ties into Dyson spheres and other sorts of stuff. So in 1961, a Soviet astronomer, Nikolai Kardashev, postulated a scale for the stages of technological advancement of civilizations based upon single source energy access and storage. So, I mean, you know, we use a lot of electrical power here on Earth, but at what point will we need so much power, so much energy that we'll need to take the entire planet as a resource and convert all of that into electrical power, be it, you know, thermal, geologic, hydropower, nuclear materials. We've taken everything we can to make it energy. We're nowhere
Solar
near that.
radiation that arrives into the planet is counted on it too.
Okay, but we haven't even gotten anywhere near that. So
I
we're,
think we're 0.7.
yeah, we're at a less than type 1, 0.7. Okay. Once you get beyond that, then you need to say, well, now we need a whole lot more energy. We're going to take our entire sun and convert its energy. Remember, this is a single source energy access and storage. So if we gather the energy from our star and it's too much for us to use right now on demand, then we're going to find a way to store it for when we need it. And that's where you get this concept of a Dyson sphere. A Dyson sphere is a sphere you build around the outside of your star to allow you to gather all the energy coming off the star and either use it now or store it and use it later. Type 3 is a galactic civilization. I don't know how you do this, but you've gathered all of the energy output of your galaxy and can store it and use it as you need it. Now, it's an arbitrary thought experiment. It's absent any observational evidence of any of this. So let's
The
just say,
Duncan experiment.
let's just say you needed a lot of energy to do what? Oh, we want to create warp drives. Okay, as we've learned more about the technology that might be associated with them, we've come down from we'll need all the energy of our galaxy to we'll need all the energy of a larger star than our star to a smaller number. So as we find out more and more about it, we don't need as much energy. Well, if your technology advances, you may not need as much energy. Think about early, large mainframe computers. How much power did they need? A lot of it. How much power does your mobile phone need? I got a battery in. Huh. So I can have a faster, more capable computer with a display, GPS navigation, Wi-Fi, 5G. It all fits in my hand, and it uses just a tiny fraction of the power of the original mainframe computers. So as the technology advances, the likelihood you're going to need to consume these massive levels of power, they may go away. So the whole scale may become a moot point. But it was an interesting thought experiment. This is one of my favorite ones. The Star Trek
Wait a
threshold.
minute, Monroe.
Yes,
Can you go
yes.
back to the last one first?
Yes.
When you started this one, you said you may have heard of this. And I'm going, I've never heard of it. That's what I said to myself. of
Well,
course.
why do you think we're
But
having
I'm
this
going-
presentation tonight?
I know, but I'm saying you said that I might have heard of it. And then I listened to your explanation of
Yep.
it. And I still don't know where I would hear of this.
Popular science fiction culture occasionally mentions the what level of civilization are they? They're a type 1. Type 1 on what? That's the Kardashev scale. So you might have heard the word, but not understood it. So that's the reason for including it tonight is this is something I thought people might have heard of, but not understand. And as you've just pointed out, you haven't even heard of it. So
Well, the thing is that sometimes you do hear of things, but
Yeah.
you don't pay attention to it because you have no idea what it is. So
Right.
you're saying where I may have heard, I was thinking maybe on a weather report, I might have heard of it.
no,
But
no,
you're
no,
not
no.
saying
More
that.
like Star
You're-
Trek and Star Wars.
Yeah,
Okay.
Or
science fiction.
ecologists like me.
But will I hear a bit in the future as a term that we would use it and hear of it?
No,
No.
it's
No, it's
more
more
it's no, it's
you
more
just
like it's more likely to go.
Civilization or-
It's more
It's-
likely to be abandoned, as it's unrealistic to expect that a civilization is going to need these levels of energy, because as we find technology advances, the energy level for use of the technology goes down dramatically.
Okay. So
you
this
know.
is not one that I'm going to hear, but if I listen to Star Trek or Star Wars in the past, they may have brought it up and now I'll know what they're referring to.
Yeah,
Yes.
they found a civilization and they say, oh, this is a type 1 civilization, something like that.
Yes.
Well, they say it's a Kardashian.
Kardashian.
No, they wouldn't mention. They just
No.
would say what type.
There is an episode of Star Trek: The Next Generation where they do mention that they're a type 2 stellar civilization on the Kardashev scale.
They do
You
mention it. Oh,
Yes,
okay.
yes. Do you remember the episode where the Enterprise found its way inside of a Dyson sphere and
Oh, yeah.
couldn't get out?
Oh, I
And
remember that.
and it required Scotty to come up with the sacrifice of his old vehicle to allow them to escape the Dyson
Lock
sphere.
the door, yeah.
Yeah.
Yes, I remember
In that
that.
episode, they mentioned that the civilization that created this was probably a type 2 on the Kardashev scale because they had a Dyson sphere.
Well, then the guy that developed the scale must have been thrilled.
I
he
don't
was
think he
long
was
dead.
alive.
He was
back then.
long
Yeah, but I
dead. He
mean,
was long
Well,
dead.
you know, in
Yeah.
spirit,
So
let's say he would have been
for
thrilled.
people who worry about the future of this own planet, the only way for us to actually reach a point of energy, because it's the structure of energy that's destroying the planet. And not just the energy that you say electrical or gas, it's also the energy for eating, calories, the whole
Yeah.
thing. So the question of the controlling the energy is that for people like me who think about the future of the planet, think about ecology, we are trying to convince people, talk about technology. So we get to a point that we are type 1 civilization, not, getting into and destroying the planet before getting into. And we are to the point of technology developed right now that we could be if there was interest.
So next up is the Star Trek thresholds for first contact. So in popular science fiction culture, there's Star Trek, which I'm not sure that anyone hasn't heard of them. But in Star Trek, more specifically in Star Trek The Next Generation series, they realized that technologically progressing a civilization before it's conquered a prescribed set of difficult to surmount hurdles, even if it's done inadvertently or accidentally, would debilitate that lesser advanced civilization and has the potential for creating threats to your own more advanced civilization through ignorant or arrogant misuse of the technology that they're exposed to. And the two examples I'll give you is don't provide Nazis with nuclear weapons early on. And as you might have seen through an episode of the original Star Trek series, don't give an early 20th century human a phaser. They'll point at their face and go, what happens when I push this button? And then they disappear. So in Star Trek, in order to make sure that nobody would pass along the advanced technology to lesser civilizations, they came up with this thing called the Prime Directive, as in everybody must obey this if you're in Starfleet. So
Maybe.
yeah, well, there were always examples. And I like to refer to it as, if you violate the Prime Directive, you may be put in jail for the rest of your life, but there's no death penalty anymore. But in order to sustain the Prime Directive, it's okay for you to sacrifice yourself and your crew to keep it a secret. So it's a double edge. But in one particular episode where they were looking at some proto-Vulcans, it's okay to have cloaking duck blinds that can malfunction, which are apparently okay for sociologists to study less advanced civilizations. Of course, with your advanced technology, you could have done so from orbit, which would have, kicked the
They
legs out.
violated that. Yeah, they violated it several times.
Oh, yes, and they always had good excuses for doing so. But having done it from orbit instead of using a duck blind, which failed, would have kicked the legs out from underneath the pretense of that episode. So they had to have an Achilles heel for the episode, and that was, don't blame us, the duck blind failed. Okay. So the most prominent threshold or great first contact filter, as in a great filter, is faster than light travel, the so-called light speed threshold for first contact. This was one that they often mention in Star Trek as, what category of civilization are they? Oh, they haven't conquered light speed travel yet, therefore keep your distance. The moment they conquered light speed travel, it's as if all the political and financial and sociological issues just would go away because they have light speed. It's more like, if they have light speed, they can come after us, so we need to talk to them. So I think that was why that threshold was chosen, because not so much for the lesser advanced species, but for the more advanced species to avoid the interlopers. But there are other technologically advanced civilizations out there that at all costs avoid contact with humans because, well, we're a warlike species. Just look at our history, or so Q thinks. But in the meantime, maybe they're just letting the duck blinds down a little bit, sort of teasing humans with a look at their tic tacs, because we're not going as fast, far forward as they think we should be. So, well, gravity manipulation doesn't exist and it'll never exist. It's an insurmountable hurdle, and faster than light travel will never exist because it's an insurmountable hurdle. Well, if we drop the duck blinds and show you, look, Tic Tac flying around, no wings, no engines, it's possible. Maybe that will give us the impetus, the motivation to, yes, it might be possible and practical. Let's spend some money developing the insurmountable hurdle technology. But who
Or
knows for
let's
sure.
steal their machines and reverse engineer.
Oh, we've got that coming up. The next one that I found as an adjunct to the Fermi Paradox was something called the Dyson Dilemma. So there are all these intelligent species out in our galaxy, and we can't see them or communicate with them. Why might that be? Well, they're a type 2 civilization. They built a Dyson sphere around their parent star, and therefore we can't see the star. Well, that just doesn't make sense to me. Does a Dyson sphere need to be a solid sphere? If it's a solid sphere, okay, well, it took time to build it. While you're building it, which might take thousands of years, it's going to have gaps in it. Or maybe you don't have to build it as a solid sphere. So we could see their starlight through the gaps, and we judge it as, well, it looks like an orange star, but it's too dim. So either it's really far away or something's blocking the star. And if the sphere is rotating, we'll see a slit of the orange light, which would give us a clue. So even if the sphere were solid, or whether it was not solid, but predominantly solid, it would absorb heat as a byproduct of converting the energy of the star to serve their purposes. So we would be able to see the Dyson sphere in infrared. And in fact, the infrared of the Dyson sphere would be more clearly focusable than the star itself, because a star is a diffuse plasma ball, whereas the infrared heat coming off of a Dyson sphere would be more sharply edged. And who's to say that a technologically advanced civilization would be required to build a Dyson sphere to get access to sufficient energy? Maybe there's other technologies that would allow them to produce more than enough energy without the insanity of a Dyson sphere. So maybe fusion, antimatter, or maybe physics we just aren't aware of and don't know about yet. Okay, now we come back to our planet. This is the Kessler Syndrome, and you've probably heard about this with regard to constellation satellites and orbital space debris and all those kinds of things, which I've mentioned before, but we'll get into a little more of the implausibility of the Kessler Syndrome and why it might not be humans that create the Kessler Syndrome. It might be a natural effect. So the Kessler Syndrome presumes that if you get enough satellites orbiting your planet, Earth, and these satellites are blown up occasionally by stupid nations like us and Russia and China, that eventually you'll put up such a debris cloud, and the debris material will be moving in all directions through all different levels of orbits, that eventually you're going to hit other satellites, and that will cause their debris to create, and you'll have a chain reaction, and the entire sphere outside the Earth's surface will be polluted by orbital debris, which will disallow you from having any other satellites in the future, and may even make it where the Earth is no longer a place where you can leave and go beyond the planet because you have to avoid all the debris. So this sort of threat of Kessler Syndrome is great if you're a competitor to Starlink, when you only have 100 satellites in orbit and Starlink has 2,000 satellites in orbit. Remember, Kessler, Kessler, Kessler. Okay, space is enormous. Orbiting objects are in numerous nested shells. Think of them as spheres within spheres. And each of those spheres actually has orbital paths, and the orbital paths actually have tilted angles. And then within each one of those paths, the satellite has separation on its station as it goes around that one line of an orbit. So what is the total area in which we can place satellites? So if you think of the Earth as a uniformly flat sphere, the surface area of a sphere is 4 pi r squared, simple math. So if you take the Earth's surface area and you calculate what that would be in square kilometers, it's 511 million square kilometers, or 197 million square miles.
Mhm.
So that's just the Earth's surface. Now, if we go to a shell that is 310 miles or 500 kilometers out, a place where, we call it low Earth orbit. This is a place, not just a single shell, but multiple shells thick, where, SpaceX puts a lot of its satellites. What is that surface area compared to the surface area of the Earth? Because we're out bigger, that sphere is going to be bigger, therefore the surface area is going to be bigger. So it goes to 594,000 square kilometers, or 594 million square kilometers, or 229 million square miles. And every shell you go out increases that surface area. The individual shells are separated by an altitude of about 19 miles. So between this shell and the next shell up is 19 miles. And you keep doing that all the way out to above geosynchronous, and geosynchronous is 35,000 kilometers. So the shell at geosynchronous is enormous. The problem with it is not all those orbits have a good return on investment, because the geosynchronous for geostationary likes to be along the equator so that you can cover the entirety of North America and South America with just one satellite. So if you were on geostationary orbit over the Pacific Ocean, there's only a couple of islands out there that you need to communicate with, and there's not enough return on that investment. So there are a lot of orbital shells and orbital stations that are just not worth the effort. But when you see graphical images of satellites in orbit, or computer simulations of satellites in orbit, they're purposefully deceptive and unrealistic of the true object size and station separations. If you were to truly represent the size of the Earth and then how big the satellites are respective to that size, the satellites wouldn't even appear. They wouldn't even be small enough to be a pixel. They'd be a small, tiny fraction of a pixel per satellite. So you just show, here's the Earth with all the satellites in orbit to scale. And you go, where are all the satellites? Well, they're there, and you just can't see them. And as an example, we have this. So these are computer simulations showing all the orbiting satellites in space junk. This is 2 different viewpoints. These are 2 different simulations. The one on the left shows more things vertically because it takes into account more different types of orbits. And you can see the geostationary equatorial orbits as being quite populated. And then as you get into low Earth orbit, it's almost a solid white sphere around the Earth. But if the Earth was really that size to scale, then these dots that are satellites would be invisible because they'd be so small. But that's not the point of the graphic. The point of the graphic is to show, looky how many satellites there are. Look how many of them there are. But in order to show you all the satellites, they've got to make the individual dots thousands of times larger than the individual satellites would be if they were drawn to the scale of Earth. So when you see these sorts of swarms and pictures and stuff, take them with a giant grain of salt and realize that if people are having a conversation about constellation satellites and they're showing you this as the threat of Kessler Syndrome, they're purposefully misleading you. But if you did want to stave off the potential for a Kessler Syndrome, how would you do that? Well, you'd want to manage and have dictates on the particular orbits and communicate that information outward. I think we covered that in the constellation satellite presentation on Yeah, you have to, when you go to launch your vehicle, you have to get approvals in order to get into that orbit because something might already be there. And if you're occupying it, we need to know that for the next time we want to launch something. So the orbital management and communication of orbital parameters is already being done. So check. You need to include deorbiting in your plans for your satellite. Well, if you went back 30 years ago, that wasn't the case, but all modern satellites that you want to launch, when you turn in your paperwork for your satellite and say, I'd like to launch this, Mr. FAA or Mr. NASA, in your orbital plan, you need something that says, please reserve enough fuel to get your butt back down and burn up. And when you burn up, make sure you've got nice metals and chemistry in your spacecraft so that it burns up good and doesn't leave any toxic residue in the Earth's atmosphere. So we're already doing that. We've got to cease deliberate destruction of satellites. No more military test firing and blowing up satellites. Just stop it. It's idiotic. Just don't do it. And we've got to come up with space tugs to deorbit unresponsive satellites. So you can have in your plan something that says, when I get to this point in the life of my spacecraft, I've got 25% fuel left. I'll use that to get myself back down and burn up. What happens if your satellite has a failure on launch, or a failure after being operational for 5 years because of a solar flare or something, micrometeoroid struck your satellite and put it out of commission and now it's wobbling or spinning? How do you get it back down? Well, turns out there's these things called space tugs that corporations are working on, which are a small fraction of the cost of a replacement bus-sized geosynchronous satellite, be it for communications or weather. So as long as it's a big, expensive satellite that costs a lot to replace, there's profit enough in building a space tug to grab a hold of the back of its engine nozzle and either push it back up or burn it back up. But it's only for the big stuff. So there's insufficient return on investment to do this for smaller satellites or for, space debris that's the size of a postage stamp but is moving at 20,000 miles an hour. So we need to start considering allocating funds for staff and the resources and technology to develop the ability to deorbit satellites and debris fields. So I think I had a presentation regarding this where if you put an almost ultraviolet, short duration, high power focusable laser in an orbit higher than geosynchronous, so it can sweep the entire planet, and you make it where it will find something you want to deorbit and just pulse the beam at it, it will, through radiation reflection pressure, push it to lower and lower orbit until it eventually burns up. So that's how you get rid of the debris field. That's how you get rid of errant satellites, is not a tug, but a pusher. But even if we do all of that, think about this. We now know that there are certain types of meteors that are junk piles. They're just loose bundles of rock and debris and, small pebbles. And if one of those things were to hit the Earth's atmosphere and just blow apart, they could create enough debris to induce a Kessler Syndrome as a natural event. So try your best. Nature comes in and says, I got a better idea. And if it did create a debris field, as solar radiation pushed on that debris, it would go to lower and lower and lower orbits. So even if it exploded at a high orbital altitude and then create a sphere around the Earth of just very far separated debris, solar radiation would eventually push that stuff lower and lower and lower. And we'll finish with my favorite one. This is kind of the opposite of Fermi Paradox and Drake's equation, is the zoo hypothesis. So if the negative result of the Fermi Paradox is proof that they don't exist because they're not talking with us, then they may have a reason for not talking with us. And the lack of contact, even though we have a high count resulting from the Drake equation could be they know better than to talk with us. So we make this arrogant human presumption that if they're out there and they're advanced, that they'd want to talk with us, the dangerous, warlike humans. More likely, they would treat us as a sociological experiment, a human ant farm, and watch us from afar. Watch us develop, see if we know what we're doing, wait until we kind of mentally cool down and stop blowing things up. Thank you for setting us back probably a few generations in the Ukraine. Not the fault of the Ukrainians, the fault of some other guy. So some might find the zoo hypothesis as insulting because it considers current human advancement as being not nearly enough. You know, we should be able to be somebody you'd want to talk to because we've got rockets and we have spacecraft and then we learn that, well, if there are that many advanced civilizations in our galaxy, and we know that the probability of life and advanced technology is pretty good, then lots of civilizations could have rudimentary space travel, but still be at war, and therefore they're good sociological experiments, and species ant farms. But as soon as we advance the technology to the point where we can become a threat to the advanced technological civilizations, as in the day the Earth stood still, the original one, not that remake. As soon as you apply nuclear power to spacecraft, we got to protect ourselves from you. Hopefully they will not want to reduce us to a burned out cinder. So at the moment, I think we're still too primitive and warlike. So for now, they'll observe us from afar and cloak their presence. And if you think duck blinds don't work, ask hunters. The creation of duck blinds that are effective is such that it dramatically increases the hunter's take because the animals go, what was that? Bang. So duck blinds do work, even to protect the watchers, but who watches the watchers? But if you wanted to breach the zoo hypothesis, how would you do this? So even if we think there is a zoo hypothesis holding us back, how is it that animals get out of zoos? Well, they could let us occasionally see through their duck blind and glimpse Tic Tacs. Doing so would let humans know there's more advanced technology that's feasible and practical, and maybe as a tease to get us to move things farther out, hopefully not in warfare. But animals can also escape the zoo. Humans are creative. We have the ability to take something that's an insurmountable hurdle and surmount it because we want to, and we put the effort into doing so. So we can develop the advanced technology thinking we do it all by ourselves, such vanity. Or we could find a crashed extraterrestrial spacecraft, pick up the parts, take them back to our labs, reverse engineer them, and create our own technology. Well, if you've watched the movie Iron Man 2, there's a quote in there from Nick Fury. You just let the little brother take your suit? This is when Rhodey came in and stole the Iron Patriot armor, when there's a lot of security that would prevent that from happening. But in order to allow him to have access to the suit, in order to allow there to be more than just him that has the suit, he deliberately allowed him to take the suit. Well, it could be that, well, if a UFO crashes, it could be through an accident, but them allowing us to take the parts left over and then reverse engineer it. If they're that advanced, I don't think they'd let us do that unless they wanted to allow us to do that. So it seems implausible that they would allow us to go, ooh, looky what crashed, scoop it all up, take it back to the lab, and then reverse engineer it into a spacecraft that might be competition for them.
Well, actually, Monroe,
Yep.
I actually when I was working in Singapore, there's quite a international community working there, and one of the guys I was working with was a Russian scientist whose job was to reverse engineer different stuff, including American stuff and computers. And he said that what they would do is they would reverse engineer and reverse engineer and reverse the American stuff and anybody's stuff until they couldn't grind down the chips to that level. When they started using more and more advanced technology, there was just no way to reverse engineer how they were laying down the circuits. So it isn't even necessarily possible to reverse engineer something.
Yeah, and that actually happened in US electronics technology. Back when we used to build circuit boards and have individual components through plated holes that we solder in, and that was how you built computer circuit boards. I've worked with Fred Lehman, and he has a tool whereby they grind down the circuit board. They would take a circuit board that they didn't have the original design specs for and reverse engineer the circuit board by grinding down the circuit board thin layer by thin layer, and then taking pictures of the etch. And they could do this for like, a 10-layer backplane and just keep grinding it down. And now you can see where all the parts go, and by the dimensions of the part you'd go, oh, that's a capacitor, that's a resistor, and then you could ohm out the various circuit paths as to where they go, and you could reverse engineer a circuit board. The moment that we started using programmable logic chips, where it was all on the stored chip and they were one-time programmable, you could no longer reverse engineer it because there weren't a lot of components on the board. If you look at it,
you wouldn't know what was in the firmware.
Right. If you look at a modern Raspberry Pi 02W computer, it's about the size of a stick of chewing gum. I think I have one right here. Yeah, there it is.
You have a stick of chewing gum?
No, I have a Raspberry Pi 0W. Here we go again with the face. So it's that small. I need a light. Let me see if I've got a light here that I can show. There we go.
Monroe, you might need to explain what a Raspberry Pi is.
It is a single board, inexpensive computer. This computer is $10. This has a 1 gigahertz processor on it. It has a half a gigabyte of memory. It supports a 32 gigabyte little flash card here at the bottom. It has the, at this end, it has the stored program on it. It is powered by USB. It has a USB connection. It has an HDMI high resolution display connection. All of that on something this size and this thick. So as we get to higher and higher density components, you can no longer reverse engineer the component, and you're just left with, well, we took it down as far as we could, and then there's the black box. And that's as far as you can go. So now you need a supply of the black boxes. And what they've taken to doing is they either put ink over the identifying marks on the chip, or they use a grinder and they grind off the top surface of the chip. And that way, when you get the computer, you can reverse engineer the circuit board, but you can't even tell what the chip is. But if the chip is running an operating system like Windows or Linux, you can ask the operating system, hey, what kind of computer chip is that? And then you just go buy them off the shelf. But in the case of more advanced technology than just computers, let's say military aircraft, the way that we deal with that with countries that don't have such advanced technology is we sell them our already superseded technology. So if you say, we have F-22 Raptors and F-35s, and we have F-35-2s, that's in our armada. That's what we have in our military in the US. But what do we sell to other countries? Oh, we sell them F-15s and F-16s. Well, why don't we sell them some of the new stuff? Oh, we don't want competition. We don't want military competition. So we'll sell them kind of like last year's goods because we know we can blow those out of the sky. So it may be that the Tic Tacs that we're now starting to see are really last year's goods, and they don't really care if we reproduce that because they've already bettered that. Okay, to the conclusions. So if we doubt our ability to create or discover prerequisite science or technology, or are not providing sufficient funding, then a hurdle will be forever insurmountable. So we're knowingly holding ourselves back by saying, oh, you'll never do faster than light. Never, 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 never. Well, maybe if you start paying attention to it and thinking about the underlying science and maybe funding the technology, you might find that it's kind of like all those other things that we conquered. You just have to apply the resources and funding it. Not so insurmountable after all. But right now it is. So if we put a major effort into stating the hurdles, and we spend all of our efforts into stating them as hurdles and propping them up as insurmountable, then presumably they will be insurmountable, at least to the fervent believers in the hurdle as being insurmountable, like faster than light. So if you ask the average person, can we go faster than light? Oh, no, we can't go currently faster than light. That's science fiction. Will we ever go faster than light? Oh, not for a really long time because it's just hard. Okay, well, we can leave it at that. But it's impractical to presume that you can control every mind on the planet to believe that insurmountable hurdles are actually insurmountable. It's analogous to, what's the phrase? Fooling everyone everywhere forever is just not going to work. You can fool some of the people some of the time, or all of the people some of the time, but you can't fool all of the people all of the time. And especially since technology these days is so fleeting because we can layer one technology on top of another one. I'm sure that IBM and Google and Honeywell believe that quantum computers will always be manufactured by large corporations and cost billions of dollars, except for that university branch in China that believes they already have a desktop, small number of qubits quantum computer that's about $50,000, quantity one. Oh, that's a problem. That lets the cat out of the bag. You will not be able to keep a technological cat in the bag forever. It might escape beyond your control and let everyone know. Then it's a matter of, can you put out enough disinformation so that they would not believe what they're hearing? If you've ever looked into the case of Bob Lazar, yeah. Well, he says he worked at Area 51, reverse engineering extraterrestrial spacecraft, and he can't fill in all the blanks. It's as if, well, he got down to the chips and couldn't understand what's inside the chips, and therefore, yes, it was doing things with gravity. Okay, but do you believe it? Well, he knew about element 115 before it was on the periodic table. Yeah, but do you believe it? He's got a weird sounding name. He works with fireworks, so he's works with explosive stuff, so he's a bad person. I don't get it. But maybe he is a disinformation expert. Maybe he isn't. Maybe you should just consider him not relevant and go ahead and take something that you believe is insurmountable and surmount it and let that just be something on the side. So never believe that something is insurmountable if you're willing to put enough resources to surmounting it. And we have a bunch of links that I'll put out there for people to gather. I'll take this and make a text file out of it and put it in the comments to the presentation when I put it up on YouTube. So, comments, questions, any terms, syndromes, paradoxes that I didn't get to?
Very nice. There are several YouTube videos on these.
Oh yeah, oh yeah. In fact, if you look at the links, Dyson Dilemma, YouTube, Kessler Syndrome,
Yeah.
wow, it's Wikipedia. Fermi Paradox, YouTube. There's some pretty good stuff out there. And in fact, earlier in the week, I sent around an email to all the Broward Astronomy audience regarding this particular YouTube video on the Fermi Paradox. It was very interesting because there's a guy out there that does called Insane Science videos.
They're
And,
they're produced by PBS.
They were produced by PBS. Now he's got separate sources of money. But whenever he's going to talk about something controversial, he can't in real time have an audience of doubting Thomases. So what he does is he enlists his wife to ask ad hoc questions. And it's really interesting to see how quickly he will blow away his staunched position, like intelligent life. And she'll say things like, what about pigs? Well, they're smart, but they're not intelligent. What about crows?
Dolphins.
What about octopus? What about dolphins? And then he's just like, oh, okay. Well, I sent a comment into them basically saying, I think what you mean is not intelligent or advanced technology. What you mean is once you have the capability to have documented science and technology, mass manufacturing, and you can layer one technology on top of another technology to create new things not found in nature in mass quantity at low cost, that's the plateau of sentient, intelligent, advanced technology, because then you can just keep moving forward with it. But if you want to say just sentient, intelligent life, could be an octopus. But they don't develop a lot. You know, they're not out there, despite the fact they have huge dexterity with their tentacled arms, and they have 8 of them. They're not out there making computers.
Their life is so short that there is no time for them to, develop.
Well, that's another
And
thing.
they're underwater. They're also underwater.
Well,
Yeah,
have you
it's
looked at
hard
some
to
of the
write down something.
have you looked at some of the studies of dolphins and their level of intelligence and what they do to play? And they are underwater.
But they can't use electricity or chemistry.
Right. But that maybe should be additional factors in the Drake equation is, do they exist in a medium that is conducive to creating technology like air versus water versus a vacuum? Or maybe, the temperature is right. It's not only going to be liquid water, it can't be boiling water. So you can always create the insurmountable hurdles for civilizations and just throw those in as more examples of the great filter as additional factors in the Drake equation to knock that big number down. Just keep knocking it down until you get to that. I can now sleep safe at night because it's a 1, and I don't have to worry about the aliens coming to get us. It's probing time.
Well, one intelligent civilization is enough for us to worry about. We don't need to worry about the aliens.
We don't even worry about the intelligence of our own civilization.
The Silurians.
The more we look for archaeological sites, the more we ignore what we actually see in front of us. So if you look at the stonework at Göbekli Tepe in Turkey, that's not carved into stone, that's relief on stone, which means you don't carve, the jaguar into the stone. You carve away everything but the jaguar, and the jaguar is now in 3D relief with shape to the body, the animal's body. That's a whole different category of carving. Yeah, but I'm sure people with copper chisels could have done that. Really? You're giving them a lot of credit. Or you go to Pumapunku and you go, yeah, everybody can make stone blocks. Can they make stone blocks to that level of precision? Can they then carve, holes through the entire length of the block that are only, like maybe less than 10 millimeters in diameter, and it's nice and cylindrical through the length of the block? Well, just ignore that. Right, because if you just ignore that, you don't have to answer the question of how they do that. So, even when we see something, I didn't see that. Don't look up, ignore the holes, ignore the grooves, ignore the fact that they fit so closely together that there's no air going between the two stones. Just ignore that stuff.
Oh, I forgot. I'm glad you mentioned that. Don't look up. Do you know what Michael deGrasse Tyson?
Neil.
That's his name?
Neil.
Yeah, Neil. That's it. I'm asleep here. Do you know what he said about don't look up?
No.
He summarized it for his audience. Said, these scientists discover and they keep telling it to the politicians and everybody, and they just ignore it and they just ignore it. And even though it's going to destroy it, they don't care anymore. He said, that's not a science fiction. That's a documentary.
Yes, I do agree with that. It was intended to be not a documentary of an asteroid coming to destroy the planet. It was intended to be an allegory for mankind destroying its existence on this planet by not tending to the environmental damage it's creating. So, yes, I think it's an allegory. It's a documentary. And this is exactly what we would do. So remember from last week's presentation, there's the new program that NASA's been given the funding to in the latest budget called CHIPS. And what is CHIPS? Well, we're going to put a satellite in cislunar orbit so it can look for the asteroids and near-Earth objects that are coming out of the direction of the sun so that we can detect them. Not that we can prevent them, just so that we can know to duck and cover. Well, that doesn't solve the problem. That just says, we're probably not going to tell you about it until it's too late, because we're not doing anything about it. I still remember the episode from the original Star Trek series where the ancient American Indian tribe had access to a repulsor beam technology that was malfunctioning. And when the asteroid was going to destroy the planet, nothing would save it until the crew of the Enterprise came in and fixed their repulsor beam and it pushed the asteroid out of the way. We need to find our repulsor beam technology. It was put here by the ancient aliens that want to make sure we live a long time. Or maybe they'll just come by when it's about to hit us and go, here, we'll take that out of your way. Or maybe they're out there in deep space nudging things without us noticing it so that nothing might ever hit us. But then we've got that big hole in Arizona that says otherwise. Maybe that was just a example.
A mistake.
No. We are about to get the quantity of humans that has enough biomass for them to extract. So our culling is coming.
Yes. It's either our culling or the troop ships are arriving to take away the slave population that they've grown. So, yeah. There's all sorts of edge conditions that can be created. So next week, Helen and I will be at Seagrape Drive in Big Cypress looking up.
I'm glad you said it because I have to charge everything and fix everything that was broken.
That's why I keep reminding both you and me. The following week, I don't have a topic yet, but I'm going to steer clear of quantum computers and artificial intelligence because I think somebody else might be interested in doing that. So I'll steer clear of those and find something else to rattle on about for 2+ hours. So are we ready for me to stop recording?
Yes.
Yeah. That would put the nail in the coffin.
Very good.